Lecture 14, Infrastructure Resilience. Theme, Cloud Security and Infrastructure Protection. Technical University of Moldova. Lecturer, Maxim Masiyutin, Associate Professor. Introduction. Welcome to Lecture 14, everyone. Today we tackle a topic that separates amateur IT operations from professional ones: infrastructure resilience. In the next 2 hours, we will explore how to design systems that not only survive failures but continue operating through them, how to recover when disasters strike, and how to build organizations that can withstand even the most severe disruptions. Let me start with a fundamental truth of computing: everything fails. Hard drives fail. Networks fail. Data centers fail. Entire cloud regions fail. The question is not whether your systems will experience failure, but when they will fail and whether you are prepared. In December 2021, Amazon Web Services experienced a significant outage in the U.S. East 1 region. This single event disrupted thousands of businesses, affecting everything from streaming services to smart home devices. Companies that had designed for resilience continued operating. Those that had not were completely offline for hours. More recently, in 2024 and 2025, we have seen several major cloud outages affecting Azure, Google Cloud, and multiple CDN providers. Each incident reinforces the same lesson: resilience is not optional, it is essential. By the end of this lecture, you will understand availability concepts, redundancy patterns, disaster recovery planning, business continuity, backup strategies, DDoS mitigation, incident response, and the emerging practice of chaos engineering. Part 1. Availability Concepts and SLAs. What is availability? Availability measures how often a system is operational and accessible. In simple terms, it is the percentage of time a system is up and working correctly. High availability is a design approach that aims to minimize downtime and ensure users can access services when needed. The formula for availability is straightforward: availability equals uptime divided by total time, multiplied by 100. If a system is down for 8 hours in a year, its availability is approximately 99.91%. But availability is more nuanced than a simple percentage. A system might be up, but responding so slowly that users cannot accomplish tasks. A system might be partially available, working for some users, but not others. True availability means the system performs its intended function within acceptable parameters. The nines of availability. In the industry, we talk about availability using nines. Each additional 9 dramatically reduces allowed downtime. 2 nines, or 99% availability, permits about 87.6 hours of downtime per year, more than 3.5 days. This is unacceptable for most business applications. 3 nines, or 99.9% availability, permits about 8.76 hours of downtime per year. This is suitable for internal applications that can tolerate occasional outages. 4 nines, or 99.99% availability, permits about 52.6 minutes of downtime per year. This is the target for most production business applications. 5 nines, or 99.999% availability, permits about 5.26 minutes of downtime per year. This is required for critical infrastructure like financial trading systems, emergency services, and core telecommunications. 6 nines, or 99.9999% availability, permits about 31.5 seconds of downtime per year. Few systems achieve this level, and doing so requires extraordinary engineering and expense. Each additional 9 typically costs significantly more to achieve than the previous one. Moving from 99.9% to 99.99% might double your infrastructure cost. Moving from 99.99% to 99.999% might increase cost by 10 times. Service Level Agreements. Service Level Agreements, or SLAs, are contracts that define the expected availability and performance of a service. Cloud providers publish SLAs for their services. AWS guarantees 99.99% availability for EC2 within a region when deployed across multiple availability zones. Azure commits to 99.95% for virtual machines with premium storage. Google Cloud promises 99.99% for compute engine in multiple zones. SLAs typically include several components. Service Level Objectives, or SLOs, define the target performance metrics. An SLO might state that 99.9% of API requests must complete within 200 milliseconds. Service Level Indicators, or SLIs, are the actual measurements. You measure request latency and compare it to the SLO. Error budgets quantify acceptable failures. If your SLO is 99.9% availability, your error budget is 0.1%, about 43 minutes per month of allowed downtime. Penalties or credits specify what happens when SLAs are not met. Cloud providers typically offer service credits, a percentage refund, when they miss their SLA. However, these credits rarely compensate for actual business losses from outages. Calculating composite availability. Real systems have multiple components. If your application depends on a database and a storage system, the composite availability is the product of individual availabilities. If your web server has 99.9% availability and your database has 99.9% availability, your composite availability is 99.9% times 99.9%, which equals 99.8%, lower than either component alone. This mathematics explains why redundancy is essential. Every dependency you add reduces theoretical availability unless you implement redundancy. Part 2. Redundancy patterns. The philosophy of redundancy. Redundancy means having backup components that can take over when primary components fail. The principle is simple: eliminate single points of failure. Any component whose failure would cause system failure is a single point of failure and must be addressed. Redundancy applies at every level: hardware, software, network, data center, and geographic region. A truly resilient system has redundancy at multiple levels simultaneously. Active-passive redundancy. In active-passive configurations, one component handles all traffic while a standby component waits idle. When the active component fails, the passive component activates and takes over. This pattern is common for databases. A primary database handles all reads and writes. A standby database maintains a synchronized copy of data. When the primary fails, the standby promotes to primary. Advantages of active-passive include simplicity and lower cost since the passive component can use fewer resources. It also avoids consistency challenges since only one component is active at a time. Disadvantages include wasted capacity in the passive component and failover time. The system is unavailable during the switchover period, which can range from seconds to minutes depending on the implementation. Database examples include MySQL replication with failover, PostgreSQL streaming replication, and SQL Server always on availability groups in synchronous mode. Active-active redundancy. In active-active configurations, multiple components handle traffic simultaneously. All components are fully operational, sharing the workload. When one fails, the others continue handling traffic, potentially with increased load. Active-active is common for web servers and application servers behind load balancers. All servers handle requests. If one fails, the load balancer routes traffic to the remaining servers. Advantages include no wasted capacity since all components work during normal operations. There is also no failover delay. The system continues without interruption when a component fails. Disadvantages include increased complexity, particularly for stateful applications. Maintaining consistency across active components requires careful design. Active-active databases, for example, must handle write conflicts when multiple nodes accept writes simultaneously. Examples include load-balanced web server clusters, multi-master database configurations like Amazon Aurora or CockroachDB, and distributed caching systems like Redis Cluster. Geographic redundancy. Geographic redundancy distributes components across different physical locations, data centers, availability zones, or regions. This protects against location-specific failures, power outages, natural disasters, network connectivity issues, or even attacks targeting specific facilities. Cloud providers offer multiple levels of geographic distribution. Availability zones are separate data centers within a region, connected by low-latency links. AZs protect against single data center failures. Most applications should deploy across multiple AZs within a region. Regions are geographically separated locations, typically hundreds of kilometers apart. Multi-region deployments protect against regional disasters or regional cloud outages. However, they add significant complexity for data consistency. Multi-cloud distribution across different providers, AWS and Azure, for example, provides protection against provider-specific outages or issues. This adds substantial operational complexity but maximum resilience. Redundancy design principles. When designing redundancy, follow these principles. Plan for N+1 minimum. If you need N components to handle load, deploy N+1 so one can fail without impact. Consider N+2 for critical systems. This allows one component to fail while another is under maintenance. Avoid shared fate. Redundant components should not share infrastructure that could cause correlated failures. Two servers in the same rack share fate if the rack loses power. Test your redundancy. Redundancy that has never been tested might not work when needed. Failover procedures should be exercised regularly. Part 3. Disaster Recovery, RTO and RPO. Defining disaster recovery. Disaster recovery, or DR, is the process of restoring systems and data after a major disruption. While high availability handles component failures automatically, disaster recovery addresses catastrophic events, data center destruction, ransomware attacks, major cloud outages, or corruption of primary systems. The goal of DR is to resume operations within acceptable timeframes and with acceptable data loss. What constitutes acceptable varies by organization and system. Recovery Time Objective, RTO. Recovery Time Objective defines the maximum acceptable time to restore operations after a disaster. RTO answers, how long can we be down? RTO varies dramatically by system criticality. For a company website, RTO might be 4 to 8 hours. The business can survive a day without a marketing website. For an e-commerce platform, RTO might be 1 to 2 hours. Every hour of downtime means lost revenue. For a trading system, RTO might be minutes. Extended outages cause financial and regulatory consequences. For life safety systems, RTO approaches 0. Emergency response systems cannot tolerate any downtime. RTO drives your DR architecture choices. Achieving a 4-hour RTO is straightforward with good backups. Achieving a 15-minute RTO requires sophisticated active-active or warm standby configurations. Recovery Point Objective, RPO. Recovery Point Objective defines the maximum acceptable data loss measured in time. RPO answers, how much data can we afford to lose? If your RPO is 24 hours, you can restore from daily backups, accepting loss of up to 1 day's data. If your RPO is 1 hour, you need hourly backups or continuous replication. If your RPO approaches 0, you need synchronous replication where every write is confirmed on both primary and DR systems before acknowledgement. Like RTO, RPO varies by system. For an archival system, 24-hour RPO might be acceptable. Historical data does not change frequently. For a transactional system, 1-hour RPO might be the maximum. Losing an hour of orders or customer interactions has significant impact. For a financial system, 0 RPO is often required. No transaction can be lost. DR strategies. Different strategies achieve different RTO and RPO combinations. Backup and restore is the simplest and cheapest approach. Take regular backups, store them off-site, and restore when needed. This achieves RTOs of hours to days and RPOs based on backup frequency. Cost is minimal, but recovery is slow. Pilot Lite maintains a minimal DR environment with core systems running but not processing traffic. When disaster strikes, you scale up the Pilot Lite environment to full capacity. This achieves RTOs of 1 to 4 hours and moderate RPOs. Cost is moderate. Warm Standby maintains a scaled-down but fully functional copy of your production environment. Traffic can be shifted to the standby with minimal changes. This achieves RTOs of minutes to an hour and RPOs approaching 0 with replication. Cost is significant but not excessive. Hot standby or active runs full production capacity in multiple locations simultaneously. There is no recovery needed. Traffic shifts automatically. This achieves RTOs and RPOs approaching zero. Cost is highest since you maintain double capacity. DR planning considerations. When planning DR, consider these factors. Document dependencies. Your application might recover quickly, but what about the authentication system it depends on? Map all dependencies and ensure DR plans address each one. Plan for partial failures. What if only some systems fail? Can you operate in degraded mode while recovering specific components? Consider human factors. Who initiates failover? How do they know when to act? Are procedures documented and practiced? Test regularly. An untested DR plan is not a plan. It is a hope. Schedule regular DR tests and learn from each one. Part 4. Business Continuity Planning. Beyond technical recovery. Business Continuity Planning, or BCP, extends beyond IT systems to encompass the entire organization's ability to continue operations during and after a crisis. While DR focuses on technology, BCP addresses people, processes, facilities, and communications. A complete business continuity program answers, if we cannot operate normally, how do we continue serving customers and fulfilling obligations? Business Impact Analysis. Business Impact Analysis, or BIA, is the foundation of BCP. BIA identifies critical business functions and determines the impact of their disruption. For each function, you assess financial impact. What revenue is lost per hour of disruption? What additional costs are incurred? Operational impact. What processes stop working? What downstream effects occur? Legal and regulatory impact. What compliance requirements are violated? What penalties might apply? Reputational impact. How do customers and partners perceive extended outages? BI results drive resource allocation for continuity planning. Critical functions with high impact per hour receive the most investment in resilience and recovery capabilities. Continuity strategies. BCP develops strategies for maintaining critical functions. Alternate work locations allow operations to continue if primary facilities are unavailable. This might mean backup offices, work-from-home capabilities, or agreements with other organizations to share space. Manual workarounds define how to perform critical functions without technology. If the order system fails, can staff take orders by phone and enter them later? Manual procedures should be documented and practiced. Third-party arrangements might allow partners or vendors to perform functions during disruptions. A competitor might handle certain services temporarily under mutual aid agreements. Communication plans ensure stakeholders know what is happening. Employees need instructions, customers need updates, and regulators may require notification. Crisis management. Crisis management provides leadership and coordination during major incidents. A crisis management team, typically including senior executives, makes decisions about declaring disasters, initiating recovery, and communicating with stakeholders. Crisis management procedures define escalation criteria. What conditions trigger crisis response? Team activation. How do team members assemble, especially outside business hours? Decision authority. Who can approve expenditures, communicate publicly, or invoke contracts? Communication protocols. How does the team coordinate and share information? Testing business continuity. Like DR, BCP requires testing. Types of tests include tabletop exercises walk through scenarios in a meeting room. The team discusses what they would do in various situations. This is low cost and identifies gaps in plans and understanding. Functional exercises actually execute specific procedures without full disruption. Staff might work from alternate locations for a day while simulating a facility loss. Full-scale exercises simulate actual disasters as realistically as possible. These are expensive and disruptive, but reveal weaknesses that other tests miss. Standards and frameworks. ISO 22301 is the international standard for business continuity management systems. It provides a framework for establishing, implementing, maintaining, and improving BCP. Certification demonstrates organizational commitment to continuity. The Business Continuity Institute and Disaster Recovery Institute International offer professional certifications and best practices for practitioners. Part 5. Backup Strategies. The foundation of recovery. Backups are copies of data stored separately from production systems. When primary data is lost, corrupted, or encrypted by ransomware, backups enable recovery. Without reliable backups, disaster recovery is impossible. Yet backup failures remain common. A 2024 survey found that 58% of organizations had experienced backup failures, preventing complete recovery. Backups that are not verified are not truly backups. They are assumptions. The 3-2-1 Backup Rule. The 3-2-1 rule is a foundational backup strategy. 3 copies of data, the original production data plus 2 backups. 2 different storage media, different types of storage to avoid media-specific failures. 1 copy offsite, stored in a different location to protect against site-level disasters. This rule has evolved for cloud environments. The 3-2-1-1-0 extension adds 1 copy offline or air-gapped, disconnected from networks to prevent ransomware spread. 0 errors, verified backups with regular restore testing. Backup types. Full backups copy all data. They are simple to restore but consume significant time and storage. Running full backups frequently is often impractical for large datasets. Incremental backups copy only data changed since the last backup of any type. They are fast and storage efficient, but restoration requires the last full backup plus all subsequent incrementals in sequence. Differential backups copy data changed since the last full backup. They take more time and storage than incrementals, but simplify restoration. You need only the last full backup plus the latest differential. Synthetic full backups combine a previous full backup with subsequent incrementals to create a new full backup without reading all production data. This reduces backup windows while maintaining restoration simplicity. Immutable backups. Immutable backups cannot be modified or deleted for a specified retention period. This protects against ransomware that targets backup systems and against insider threats or administrative errors. Implementation options include worm storage, write once, read many, physically prevents modification. Object lock in cloud storage, S3 object lock, Azure immutable blob storage, prevents deletion via API. Air-gapped storage with physical disconnection from networks eliminates remote attack vectors. Backup application features that enforce immutability through software controls. Immutability has become essential. Modern ransomware specifically targets backup systems to prevent recovery. The 2024 and 2025 ransomware landscape shows attackers routinely destroying or encrypting backups before deploying ransomware on production systems. Backup verification. Backups must be verified regularly. Verification includes integrity checks confirm backup data is not corrupted. Most backup systems include checksums or hash verification. Restore testing actually recovers data from backups. You should regularly restore files, databases, and entire systems from backups to verify the process works. Recovery time testing measures how long restoration actually takes. Your RTO assumptions should be validated through testing. Application testing confirms recovered systems function correctly. A database that restores without errors might still have application-level issues. Cloud backup considerations. Cloud environments require adapted backup strategies. Native cloud backup services, AWS Backup, Azure Backup, integrate with cloud resources but may not provide complete protection. Cross-region replication protects against regional failures but does not protect against logical corruption that replicates. Cross-account backups protect against account compromise by storing backups in separate AWS accounts or Azure subscriptions. Egress costs can be significant when restoring large amounts of data from cloud storage. Include these costs in DR planning. Verify cloud provider backup SLAs. Cloud providers often do not back up your data automatically. It is your responsibility. Part 6. DDoS attack types and mitigation. Understanding DDoS. Distributed denial of service attacks attempt to make services unavailable by overwhelming them with traffic or requests. Unlike single-source DOS attacks, DDoS attacks come from many sources simultaneously, often thousands or millions of compromised devices and botnets. DDoS attacks have grown in scale and sophistication. The largest attacks now exceed 1 terabit per second of traffic. The 2023 to 2025 period has seen record-breaking attacks, with some exceeding 3 Tbps. No single organization can absorb such attacks without specialized protection. Volumetric attacks. Volumetric attacks flood networks with traffic, consuming bandwidth and preventing legitimate traffic from reaching targets. Common volumetric attacks include UDP floods send massive amounts of UDP traffic to random ports. The target's resources are consumed responding to the traffic. ICMP floods use ping requests at massive scale. Also known as ping floods, these consume both bandwidth and processing resources. Amplification attacks exploit protocols that return larger responses than requests. The attacker sends small requests with spoofed source addresses, the victim's address, and the amplifiers send large responses to the victim. DNS amplification can multiply traffic by 50x or more. NTP amplification can achieve even higher ratios. Protocol attacks. Protocol attacks exploit weaknesses in network protocols to consume server resources or intermediate equipment capacity. SYN floods exploit the TCP handshake. Attackers send connection requests, SYN packets, but never complete the handshake, leaving connections half-open and exhausting server resources. Fragmented packet attacks send malformed or overlapping packet fragments that consume resources when the target tries to reassemble them. SMUF attacks use ICMP broadcast requests to networks that respond to the victim's spoofed address. Application layer attacks. Application layer attacks, also called Layer 7 attacks, target specific applications with requests that appear legitimate but consume excessive resources. HTTP floods send valid HTTP requests at massive scale. Each request requires server processing, database queries, and response generation. Slow LORRI's attacks open connections to web servers and send partial requests extremely slowly, keeping connections open indefinitely and exhausting connection pools. Application-specific attacks target resource-intensive functions. An e-commerce site might be attacked through expensive search queries or report generation. DDoS mitigation strategies. Mitigation requires a layered approach. Over-provisioning maintains excess capacity to absorb attacks. This is expensive and limited. You cannot provision for multi-terabit attacks. Rate limiting restricts requests from individual sources. This helps with smaller attacks, but does not address distributed attacks with many sources sending few requests each. Content delivery networks distribute traffic across global networks. CDNs absorb volumetric attacks by spreading load across their massive infrastructure. DDoS mitigation services from providers like Cloudflare, Akamai, AWS Shield, and Azure DDoS Protection analyze traffic and filter attacks before they reach your infrastructure. These services use machine learning to distinguish attack traffic from legitimate users. Anycast routing distributes traffic to multiple data centers. Attacks are diluted across locations rather than concentrated on a single target. Upstream filtering works with ISPs and hosting providers to filter attack traffic before it reaches your network. Cloud-native DDoS protection. Cloud providers offer integrated DDoS protection. AWS Shield standard provides automatic protection against common volumetric and protocol attacks at no additional cost. Shield Advanced adds application layer protection, dedicated support, and cost protection. Azure DDoS protection provides volumetric and protocol attack mitigation integrated with Azure networking. Google Cloud Armor provides DDoS protection and web application firewall capabilities. These services are essential for cloud deployments. Enable them and configure them appropriately for your applications. Part 7. Incident response in cloud environments. Cloud incident response challenges. Incident response in cloud environments differs from traditional on-premises response. You do not have physical access to servers. Evidence may be ephemeral. Terminated instances leave no disk images. Multiple parties share responsibility for detection and response. Yet the fundamentals remain: preparation, detection, analysis, containment, eradication, recovery, and post-incident activity. The implementation changes, but the process remains. Preparation for cloud incidents. Preparation is even more critical in cloud environments. Enable comprehensive logging. Cloud services generate logs, but you must enable and configure them. AWS CloudTrail logs API calls. Azure Activity Logs record resource operations. Google Cloud Audit Logs track administrative actions. Centralized logs. Ship logs to a central location, a SGM, a dedicated logging account, or a log management platform. Attackers may delete logs in compromised accounts. Centralized logging preserves evidence. Establish baseline behavior. Know what normal looks like so you can identify anomalies. Use cloud-native tools like AWS GuardDuty, Azure Defender, or Google Cloud Security Command Center. Define response procedures for cloud-specific scenarios. Compromised IAM credentials, exposed storage buckets, cryptomining on compromised instances. Establish relationships with cloud provider security teams. Major providers have dedicated incident response contacts for serious incidents. Detection in cloud environments. Detection relies on multiple sources. Cloud security services provide automated threat detection. GuardDuty detects reconnaissance, instance compromise, and account compromise. Azure Defender identifies threats across Azure services. SGM correlation combines cloud logs with other data sources to identify patterns indicating compromise. Custom detection rules address organization-specific threats. Monitor for unusual API calls, unexpected geographic access, or resource creation in unused regions. Billing alerts can detect cryptomining. Unexpected compute charges often indicate compromised instances being used for cryptocurrency mining. Containment and eradication. Cloud environments enable rapid containment. Revoke compromised credentials immediately. IAM users, access keys, and service account keys can be disabled instantly. Isolate compromised resources using security groups or network ACLs. Do not terminate instances immediately if you need them for forensic analysis. Snapshot compromised instances for forensic investigation before termination. You can analyze snapshots in isolated environments. Review and revoke third-party access. Compromised accounts may have granted persistent access through federation or cross-account roles. Recovery in cloud. Recovery leverages cloud capabilities. Redeploy from known good templates. Infrastructure as code enables rapid recreation of clean environments. Restore from verified backups. Confirm backups are not affected by the same compromise. Implement additional controls to prevent recurrence before restoring service. Monitor closely during recovery. Attackers may have established persistence mechanisms that survive initial cleanup. Post-incident activity. Cloud incidents require thorough post-incident analysis. Preserve all evidence for potential legal or regulatory proceedings. Conduct root cause analysis. How did attackers gain access? What controls failed? What detection gaps existed? Update procedures and controls based on lessons learned. Share appropriate information with cloud providers. They may have insights or need to address issues affecting other customers. Consider whether regulatory notification is required. GDPR and NIS2 and other regulations mandate breach notification within specific time frames. Part 8. Chaos engineering. Intentional failure. Chaos engineering is the practice of intentionally introducing failures to verify system resilience. Instead of waiting for failures to happen, we cause them deliberately under controlled conditions to learn how our systems behave and how to improve them. Netflix pioneered chaos engineering with Chaos Monkey, a tool that randomly terminates production instances. If systems are resilient, users never notice. If systems fail, engineers learn where improvements are needed. The Chaos Engineering Principles. The principles of chaos engineering, published by Netflix and the chaos engineering community, define the practice. Build a hypothesis around steady-state behavior. Define what normal looks like. successful transactions, response times, error rates. Very real-world events. Introduce failures that could actually occur. Server crashes, network partitions, latency injection, dependency failures. Run experiments in production. Simulated environments may not reveal production issues. Carefully controlled production experiments provide the most realistic results. Automate experiments to run continuously. Resilience should be verified regularly, not just once. Minimize blast radius. Start with small experiments and limited scope. Expand as confidence grows. Chaos engineering tools. The chaos engineering ecosystem has matured significantly. Chaos Monkey terminates random instances in AWS. Part of Netflix's Simian Army. Gremlin provides a commercial platform for chaos experiments across various infrastructure types. Litmus Chaos is an open-source chaos engineering platform for Kubernetes environments. AWS Fault Injection Simulator provides managed chaos engineering for AWS resources. Azure Chaos Studio offers similar capabilities for Azure environments. Chaos Mesh is a cloud-native chaos engineering platform for Kubernetes. Types of chaos experiments. Common chaos experiments include: instance termination verifies applications handle lost nodes. Network latency injection tests timeout handling and user experience under slow conditions. Network partition simulates split-brain scenarios where components cannot communicate. CPU and memory stress tests behavior under resource exhaustion. Dependency failure simulates unavailable databases, APIs, or other dependencies. DNS failure tests behavior when name resolution fails. Clock skew introduces time drift to identify time-sensitive logic failures. Implementing chaos engineering. Start chaos engineering gradually. Begin in pre-production. Run chaos experiments in staging environments until you have confidence in your systems and processes. Start with known resilience. Your first experiments should test mechanisms you believe are working. Verify your assumptions before probing unknown areas. Establish clear abort conditions. Define what constitutes unacceptable impact and ensure experiments can be stopped immediately. Communicate broadly. Teams should know when chaos experiments are running. Surprises lead to mistrust. Document and share results. Chaos experiments generate valuable learning that should benefit the entire organization. Chaos engineering and resilience culture. Chaos engineering is as much about culture as technology. It normalizes talking about failure. It shifts thinking from "will this fail?" to "when this fails, what happens?" It builds confidence through evidence rather than hope. Organizations practicing chaos engineering report fewer production incidents, faster recovery times, and increased confidence in their system's resilience. Part 9. Practical exercises and case studies. Exercise 1. Availability calculation. Calculate the composite availability of a system with the following components. Web server cluster, 99.95% availability. API gateway, 99.99% availability. Database, 99.9% availability. Cache, 99.95% availability. Solution, 0.9995 times 0.9999 times 0.999 times 0.9995 is equal to 0.9979 or 99.79% availability. This system has less than 3 nines of availability. To improve, you would add redundancy to the lowest availability component, the database. Exercise 2. RTO and RPO Analysis. For each system below, propose appropriate RTO and RPO values and justify them. Public marketing website, internal HR system, real-time payment processing system, customer support ticketing system. Consider business impact, regulatory requirements, and technical feasibility. Exercise 3. Backup strategy design. Design a backup strategy for a healthcare organization's electronic health record system. Consider regulatory requirements, HIPAA, data sensitivity, recovery requirements, ransomware protection. Case study, GitLab database incident, 2017. In January 2017, GitLab experienced a database incident that resulted in loss of production data. An engineer accidentally deleted the production database during troubleshooting. When they attempted to recover, they discovered multiple backup systems had failed. Regular backups had not been completing successfully. Replicas were far behind the primary. Point-in-time recovery was not configured. Backup verification had not been performed. GitLab lost approximately 6 hours of data and experienced 18 hours of downtime. Lessons learned. Verify backups through regular restore testing. Monitor backup systems actively. Do not rely on a single backup method. Document and practice recovery procedures. GitLab responded admirably by documenting the incident publicly and implementing comprehensive improvements. Case study: AWS US East 1 outage, 2017. In February 2017, a typo in a maintenance script took down a significant portion of S3 in the US East 1 region. The cascading effects were enormous because so many services depended on S3, including AWS' own status dashboard. Lessons learned. Dependencies on shared services can cause correlated failures. Status dashboards should not depend on the systems they monitor. Multi-region architectures provide protection against regional issues. Even cloud giants can have major outages. Conclusion. Let me summarize the key concepts from today's lecture on infrastructure resilience. We began with availability concepts and SLAs. Availability is measured in nines, with each additional 9 dramatically reducing allowed downtime and increasing cost. SLAs define expectations through SLOs, SLIs, and error budgets. Composite availability is the product of component availabilities. Redundancy patterns eliminate single points of failure. Active-passive provides simple failover with some downtime. Active-active maintains continuous operations through failures. Geographic redundancy protects against location-specific events. Disaster recovery planning defines how to restore operations after catastrophic events. RTO defines maximum acceptable downtime. RPO defines maximum acceptable data loss. Different DR strategies achieve different RTO and RPO combinations at different costs. Business continuity planning extends beyond IT to encompass the entire organization. Business impact analysis identifies critical functions. Continuity strategies maintain operations through alternate means. Crisis management provides leadership during incidents. Backup strategies follow the 3-2-1-1-0 rule. Immutable backups protect against ransomware. Verification through regular restore testing is essential. DDoS attacks come in volumetric, protocol, and application layer varieties. Mitigation requires layered defenses including CDNs, cloud-native protection, and specialized services. Incident response in cloud environments requires preparation through logging, detection through cloud security services, and leveraging cloud capabilities for rapid containment and recovery. Chaos engineering intentionally introduces failures to build confidence in resilience. It normalizes discussions about failure and creates a culture of continuous improvement. For your preparation, review your organization's or a familiar organization's DR plan. Calculate composite availability for a system you use. Consider how chaos engineering principles might apply to systems you work with. In our next lecture, we will explore security risk management, how to identify, assess, and treat security risks systematically. Discussion questions. How should organizations determine the appropriate level of availability investment for different systems? What lessons can be drawn from major cloud provider outages about infrastructure resilience planning? How can chaos engineering practices be safely introduced into organizations that are risk-averse? Thank you for your attention. Are there any questions? Review questions. Explain the concept of nines of availability and calculate the annual downtime for 99.99% availability. Compare active-passive and active-active redundancy patterns. What are the trade-offs of each? Define RTO and RPO. How do they influence disaster recovery strategy selection? What is the 3-2-1-1-0 backup rule? And why was it extended from the original 3-2-1 rule? Describe the 3 categories of DDoS attacks and the mitigation strategies for each. What is business impact analysis, and how does it inform business continuity planning? Explain chaos engineering principles and describe 3 types of chaos experiments. What lessons does the GitLab 2017 database incident teach about backup verification? Key terms. Active-active, a redundancy pattern where all nodes handle traffic simultaneously. Active-passive, a redundancy pattern where standby nodes take over when primary nodes fail. BCP, business continuity plan, ensuring critical functions continue during and after a disaster. BIA, business impact analysis, identifying critical business functions and their dependencies. CDN, content delivery network, a distributed system for delivering content with improved performance and DDoS protection. Chaos engineering, the practice of intentionally introducing failures to test system resilience. DDoS, distributed denial of service, an attack overwhelming systems with traffic from multiple sources. DR, disaster recovery, restoring IT systems and data after a catastrophic event. Error budget, the acceptable amount of downtime or errors within an SLA period. High availability, system design ensuring a specified level of operational continuity with minimal downtime. Immutable backup, a backup that cannot be modified or deleted after creation. Load balancing, distributing network traffic across multiple servers to ensure reliability and performance. RPO, recovery point objective, the maximum acceptable amount of data loss measured in time. RTO, recovery time objective, the maximum acceptable duration of system downtime. SLA, service level agreement, a formal commitment to performance standards. SLI, service level indicator, a quantitative measure of service performance. SLO, service level objective, a target value for a service level indicator. References and further reading. NGSD SP 800-34, Contingency Planning Guide for Federal Information Systems. ISO 22301:2019 Business Continuity Management Systems. AWS Well-Architected Framework, Reliability Pillar. Azure Architecture Center, Reliability. Google Cloud Architecture Framework, Reliability. The Practice of Cloud System Administration, Limoncelli, Chalop, Hogan. Principles of Chaos Engineering, Netflix. Site Reliability Engineering, Google. CISA DDoS Attack Guidance. Cloud Security Alliance, Security Guidance v4.